Hello viewers, today is the time for the presentation of video lecture 10 of the pavement construction. Under this video, chemical properties of aggregate is going to be presented. Now let us see the chemical properties of aggregate. Aggregates are typically composed of various minerals such as quartz, feldspar, calcite, and mica. These minerals contribute to the overall chemical composition of aggregate. Quartz, for example, is common mineral found in aggregate and is composed of silicon dioxide. Feldspar, another common mineral, consists of aluminum silicate with varying amount of potassium, sodium, and calcium. Calcite, which is a form of calcium carbonate, can also be present in aggregates, and mica, a mineral group that includes muscative and biotite, adds to the chemical makeup of aggregate with its aluminum silicate structure. In general, chemical composition of aggregate can vary depending on the specific type of minerals present in the aggregate. It is important to analyze the chemical composition of aggregate to ensure they meet the desired quality standard for use in construction and other applications. Now, let us see alkali aggregate reaction. Alkali aggregate reaction, also known as AAR, is a chemical reaction that occurs in concrete structure between the alkaline cement paste and reactive minerals present in certain aggregates. The reaction can cause significant damage to concrete structures over time. The main types of alkali aggregate reactions are alkali silica reaction, ASR, and alkali carbonate reaction, ACR. In alkali silica reaction, reactive silica in aggregate reacts with alkalines in the cement paste to form a gel-like substance that absorb water and swell, and leading to crack and deterioration of the concrete. Alkali carbonate reaction occurs when certain carbonates rock in the aggregate react with alkalis to form expansive products, causing similar damage. To mitigate the effect of alkali aggregate reaction, preventive measures can be taken during the design and construction of concrete structure. This can include using low alkali cement, selecting non-reactive aggregate, and adding supplementary cementitious materials to the concrete mix. Regular monitoring and maintenance of concrete structures are also crucial to detect and address any sign of alkali aggregate reaction early on. By understanding and managing alkali aggregate reaction, structures can be built to be more durable and long-lasting. Now, let's see the mechanism of deterioration of concrete through the alkali aggregate reaction. The mechanism of deterioration through alkali aggregate reaction can be summarized as follows. Alkali, such as sodium and potassium, react with the silica or carbonate minerals present in the aggregate. This reaction forms a gel-like substance within the concrete, which absorbs water and expands over time. The expansion of the gel exerts pressure on the surrounding concrete, leading to crack and deterioration of structure. The crack allows for further penetration of water and aggravating the reaction and causing additional damage. Preventive measures against alkali reaction includes using low alkali cement, selecting non-reactive aggregate, and adding mineral admixtures such as fly ash or silica fume to mitigate the reaction. Regular monitoring and testing for alkali aggregate reaction in structures can also help to prevent deterioration and ensure the longevity of concrete structures. Let us see the control of alkali aggregate reaction. Alkali aggregate reaction is a chemical reaction that occurs when alkalis react with certain minerals present in some aggregate and used in concrete. This reaction can lead to the formation of gel-like substance, as we have said before, and this causes expansion and cracking of the concrete over time. There are several methods to control alkali aggregate reaction in concrete construction using low alkali cement. By using cement with lower alkali content, the potential for the reaction to occur can be minimized. The second one is selecting suitable aggregates. Avoiding using aggregates that are known to react with alkali can help prevent alkali aggregate reaction. Testing aggregate for potential reactivity before use is important. The third one is adding mineral admixture. Incorporating supplementary cementitious material such as fly ash, sludge, or silica fume can help mitigate alkali aggregate reaction. Fourth, using reactive inhibitors. Certain chemicals can be added to concrete mix to inhibit the reaction between alkalis and aggregates. Fifth, providing proper curing. Ensuring proper curing of concrete can help reduce the risk of alkali aggregate reaction by promoting proper hydration and reducing the permeability of the concrete. By implementing these control measures, engineers and construction professionals can minimize the risk of alkali aggregate reaction and ensure the durability and longevity of concrete structure. Now let us see the thermal property of aggregate. Aggregates are commonly used in construction for various purposes such as concrete production, road construction, and drainage system. Understanding the thermal properties of the aggregate is essential in ensuring the durability and performance of these structures. The thermal property of aggregate include thermal conductivity, specific heat capacity, and thermal expansion. Thermal conductivity refers to the material's ability to conduct heat, while specific heat capacity is the amount of heat required to rise the temperature of the unit mass of material by 1 degree Celsius. Thermal expansion is the increase in volume of the material as its temperature increases. So the thermal conductivity of aggregates varies depend on their composition and moisture content. Generally, aggregate with higher thermal conductivity provides better heat transfer in structure such as concrete slab and road pavement. The specific heat capacity is important in determining how aggregates will respond to temperature change. Aggregates with high specific heat capacity can absorb and release heat slowly, helping to regulate temperature fluctuation in the structure. Thermal expansion. Thermal expansion of aggregate is crucial in preventing cracking and damaging to structures due to temperature change. Aggregate with high thermal expansion coefficient may cause strain on the structure as they expand and contract with temperature variations. In conclusion, understanding the thermal properties of aggregate is crucial in ensuring the long-term performance and durability of construction materials. By considering factors such as thermal conductivity, specific heat capacity, and thermal expansion, engineers and designers can make informed decisions in selecting the appropriate aggregate for their projects. Now let us see the above mentioned thermal properties of aggregate, which are thermal conductivity, specific heat capacity, and thermal expansion. Thermal conductivity. Thermal conductivity is an important property of aggregate that impacts the overall performance of construction materials. In this lecture, we will dive into the concept of thermal conductivity and its significance in the context of aggregate. When you define thermal conductivity, it refers to the ability of the materials to conduct heat. It is essentially a measure of how well a substance can transfer heat through its mass. In the case of aggregates used in construction, thermal conductivity plays a crucial role in determining the thermal behavior of the composite material. Factors affecting thermal conductivity. 1. Particle size. Finer aggregates tend to have lower thermal conductivity compared to coarse aggregates due to their higher surface area. Second one is porosity. Higher porosity in aggregate can lead to increased thermal conductivity as air void acts as thermal bridges. Third, moisture content. The presence of moisture in aggregate can significantly alter their thermal conductivity as water conducts heat more efficiently than solid materials. Importance of the thermal conductivity. Understanding the thermal conductivity of aggregate is essential in designing energy efficient building. By incorporating aggregate with appropriate thermal properties, construction can optimize the thermal performance of structure and leading to reduced energy consumption and lower operation costs. In conclusion, thermal conductivity is a critical property of aggregate that influence the thermal behavior of construction materials. By considering factors such as particle size, porosity, and moisture content, builders can make informed decisions to enhance the energy efficiency of any building. Let us see the specific heat capacity of the aggregate. The specific heat capacity is the measure of the amount of heat energy required to rise the temperature of a mass of substance by 1 degree Celsius. The specific heat capacity of aggregate can vary depending on the type of aggregate used. In general, the specific heat capacity of most aggregate ranges from about 0.2 up to 0.9 kilojoule per kilogram per degree centigrade. However, it is important to note that specific heat capacity value can also be influenced by factors such as moisture content, particle size, and mineral composition of the aggregate. When using aggregate in construction or in industrial process, understanding is its specific heat capacity is important for calculating energy requirement and optimizing heat transfer process. It can also help in designing efficient thermal management system. Let's see the thermal expansion of aggregate. Thermal expansion refers to the tendency of material to increase its volume as they are heated. This phenomena is crucial to consider the construction material, such as aggregates, which are often subjected to fluctuation of temperature. First, let us define what aggregate is. Aggregate is a granular material used in construction, such as sand, gravel, crushed stone, or recycled concrete. It plays a crucial role in the strength and durability of concrete, asphalt, and other building materials. Effect of temperature on aggregate. When aggregate is exposed to temperature change, it undergoes thermal expansion. As the temperature rises, the particles within the aggregate expands and move apart from each other. Conversely, when the temperature decreases, the particles contract and move close together. In conclusion, the thermal expansion of aggregate is critical factor to consider in construction projects. If not accounted for, the expansion of and contraction of aggregate can lead to cracking, spalling, or even structural failure in building and roadways. Proper design and material selection are essential to mitigate these risks. Strategies which has to be addressed for thermal expansion. To address the thermal expansion of aggregate, engineers and contractors can utilize various strategies. They may include using aggregate materials with lower coefficient of thermal expansion, incorporating expansion joint in structure, and designing flexible pavement system to accommodate temperature fluctuation. In general, understanding the thermal expansion of aggregate is essential for ensuring the longevity and safety of construction projects. By considering this phenomena and implementing appropriate measures, engineers can design structures that withstand temperature change and maintain their integrity over time. Thank mechanical property. Aggregates are commonly used in construction to create concrete, asphalt, and other building materials. Understanding the mechanical property of aggregate is essential for ensuring the quality and durability of this structure. One important mechanical property of aggregate is their strength. This can be measured using tests such as compressive strength test, which determines the ability of an aggregate to withstand compressive load. A higher compressive strength indicates a stronger aggregate that is more suitable for the high-duty construction project. Another key mechanical property is aggregate's abrasion resistance. This refers to the ability of the aggregate to resist wear and tear from friction and impact. Aggregate with high abrasion resistance are ideal for road construction and other applications where they will be subjected to constant traffic and weathering. The shape and texture of aggregate also play a role in their mechanical property. Angular aggregates with rough texture tends to interlock together, providing greater stability and strength in the final product. On the other hand, round aggregates may be more workable but can lead to reduced cohesion in the concrete mix. In addition to strength, abrasion resistance, and shape, other mechanical properties of aggregate include toughness, elasticity, and porosity. These properties impact the overall performance of concrete or asphalt mix and can affect the long-term durability of the structure. By understanding and testing the mechanical property of aggregate, engineers and construction professionals can select the right material for their project and ensuring safety, longevity, and cost effectiveness. Let's see strengths. The strength of aggregate plays a crucial role in determining the overall strength and durability of concrete. Aggregates are inert materials mixed with cement and water to form concrete, and their strengths directly impact the strength of the final product. There are different types of strengths associated with aggregates, including compressive strengths, tensile strengths, and flexural strengths. Compressive strength is the most commonly measured strength of aggregate and refer to the ability of the materials to withstand compressive force. Tensile strength, on the other hand, measures the ability of aggregate to resist tension, while flexural strength measures the material's ability to resisting bending. These strengths are important in determining the suitability of aggregate for various applications. Factors that influence the strength of aggregate include the type of rock from which they are derived, the gradation of particles, the shape and texture of particles, and the presence of deleterious materials, and aggregate with strong, durable particles that are well graded and have a smooth surface tend to produce concrete with high strength. It is essential to test the strength of aggregate before using them in concrete to ensure that they meet the required specifications, and varying standard tests such as the Los Angeles abrasion test and the aggregate crushing value test can be conducted to assess the strength of aggregate accurately. In conclusion, the strength of aggregate is a critical factor on determining the overall strength and durability of concrete. By selecting high-quality aggregate with appropriate strength characteristics, engineers and construction professionals can ensure the longevity and performance of the concrete structure. Toughness. Aggregates are materials such as gravel, sand, and crushed stone that are used in construction for making concrete and asphalt. The toughness of aggregates refers to their ability to resist fracture under loading conditions. Higher toughness indicates that the aggregate can withstand more stress before breaking. The toughness of aggregate is an important factor in determining their suitability for use in construction projects. Aggregates with high toughness are able to resist crack propagation and withstanding heavy loads without breaking. Toughness is typically measured using the Los Angeles abrasion test, which subject to aggregates to abrasion and impact to simulate the wear and tear by the wear and tear they will experience in real world conditions. Aggregate with high toughness are preferred for high traffic areas such as highway and airport runways, where they will be subjected to heavy loads and frequent uses. The toughness of aggregate can also affect the durability and longevity of the concrete structure. As aggregates, they are more resistant to fracture will help the concrete maintain its integrity over time. In general, the toughness of aggregate plays a crucial role in the performance and durability of construction materials. Engineers and architects must carefully consider the toughness of aggregate when selecting materials for their project to ensure that they meet the necessary strength and durability requirements. Hardness Hardness of aggregate refers to the ability of the aggregate materials to resist wear and abrasion. It is an important property to consider in construction projects as it can impact the durability and performance of the final product. The hardness of aggregate is typically measured using the Mohs scale, which ranks minerals according to their relative hardness on a scale from 1 to 10. 1 tell and 10 is diamond. In construction industry, aggregates with higher hardness rating are then preferred as they are more resistant to wear and erosion. This can help to ensure that the final product, such as road or building, maintains its structural integrity over time. Aggregate hardness can also impact the overall quality of the construction material, as softer aggregates may break down more easily under pressure or heavy loads. To test the hardness of aggregates, various methods can be used, including the Mohs scale, the Los Angeles abrasion test, and the micro devil tests. These tests can help to determine the suitability of aggregate for specific construction applications and ensuring that the final product meets the required standard for durability and performance. In general, the hardness of aggregate is an important factor to consider in construction projects as it can impact the durability and performance of the final product. By testing the selecting aggregate with the appropriate hardness rating, engineers and builders can ensure the long-term success for their construction project. Bond strength of concrete. Bond strength of concrete refers to the adhesive strength between aggregate particles and the surrounding cement paste in concrete. This bond strength is crucial for the overall strength and durability of the concrete structure. There are several factors that can influence the bond strength of aggregate, including the surface texture of the aggregate particles, the presence of any contaminants or dust on the surface, the moisture content of the aggregate, and the type of aggregate used. To determine the bond strength of aggregate, various test methods can be employed, such as pull-out test, the bond stress test, or the direct tension test. These tests measure the force required to pull the aggregates particles out of the surrounding cement paste and providing valuable information on the bond strengths at the interface. Proper surface preparation of the aggregate using clean and well-graded particle and ensuring adequate compaction during concrete placement can help improve the bond strength of aggregate in concrete structure. In general, understanding and optimizing the bond strength of the aggregate is essential for ensuring long-term performance and durability of concrete structure. This is all about today. Thank you for your attention.